This is Dr. Lewis going over some material for the course on conjugation. This was one of the examples which demonstrates, if you like, the power of conjugation or resonance. So here we have a molecule. It says, give a curly arrow mechanism that accounts for the following reaction. Explain the driving force for the reaction proceeding from left to right. So we can see that that's a non-conjugated system, double bond separated from another double bond by CH2, and there we've got a conjugated system. And in order for the reaction to happen, we've got sulfuric acid, so it's basically a source of H+. It's a strong acid. So we're going to use protons to catalyze the reaction, and so the very first step is going to be protonation of the double bond. So we're going to draw that molecule and place an H+ near one of the double bonds. So it can either protonate on the end to give a tertiary carbocation, which is stable, or protonate at this carbon, which will give us very unstable primary carbocation. So it's going to obviously go at the end. So I'll push the curly arrow from the double bond through the end where it joins onto the proton, just to show that just designates where it joins. So following that, we've now lost that double bond and we've formed a new sigma bond to H, and that gives us our carbocation there. Now, we could just lose the proton from the same position and return back to our starting material. But instead of losing the proton from here in a reversible fashion, we just, instead of that, we lose a proton from the other side of the carbocation. And if we do that, the double bond now ends up here in conjugation with that double bond. So now I'll just not bothered writing the H anymore. So there we've got a conjugated system. But see, the product is the double bond is not in exocyclic, it's endocyclic in the ring. So we do a further protonation, and again we draw the same. I'll do the same curly arrow going through the end that it joins. Draw the rest of the molecule, and now we've got another stable carbocation. And now we're going to use one of these two H's here and draw a nice long bond, so you can draw the curly arrows quite easily from either of those two. So that curly arrow says that the pair of electrons from the CH bond is forming that double bond, and H+ will be lost. So that's the mechanism. It's just protonation followed by the reverse deprotonation. But it just so happens that the deprotonation is not from the same position, it's from a different side, a different carbon next to. So it's got to be next to the carbocation. It can't be ever on the carbocation. So it could be here, it could be there, it could be there. But if you lose it from this position, you're going to get into conjugation with that. So why is it? What's the driving force? Well, we can say, draw better colours than that. We can say, we can show the conjugation. So that pair of electrons goes into here, leaving behind a positive charge, and the negative charge ends up on that carbon here, which is there. So the driving force is going from non-conjugated diene to more stable conjugated diene. And another factor is we're going from di-substituted double bonds to tri-substituted bonds. So plus forms more stable one, two, three tri-substituted double bonds.